I set up a Suzuki coupling. The Suzuki reaction is a palladium-catalyzed cross-coupling between organoboronic acids or esters and organic halides or triflates under basic conditions to form a new carbon-carbon sigma bond. Carbon-carbon bond formation reactions are essential for the development of bioactive molecules, agrochemicals, and drugs. These types of reactions, known as cross-coupling reactions, have been some of the greatest breakthroughs in organic and organometallic synthesis since the discovery of catalysis. Many of these transformations would not be possible without transition metal-based catalysts such as nickel and palladium, which are preferred due to their ease of exchange of redox states, nickel to nickel 0 and palladium to palladium 0. The reactions are so important in the field of chemistry that they were recognized with the award of the Nobel Prize in Chemistry in 2010 to three of their main developers, Heck, Negishi, and Suzuki. Since the Suzuki-Miyaura cross-coupling reaction was discovered in 1979, many studies have been conducted showing that the combination of the base, the solvent, and the catalyst can affect the yields and selectivity of the reaction. Some research efforts have focused on developing novel catalysts based on first-row transition metals such as iron, copper, and nickel due to their greater availability and terrestrial abundance compared to those of palladium. Nonetheless, palladium-based catalysts remain the optimal choice for the majority of cross-coupling reactions. This transformation follows a well-defined catalytic cycle based on three steps. First, oxidative addition of the palladium-0 complex to the organic halide occurs. Here, the bond between the heteroatom and the organic group is broken, and two new bonds are formed with the palladium complex, oxidizing the metal. The oxidation state of the metal increases by 2 units, from palladium 0 to palladium 2. Next, transmetalation between this intermediate and the boronate occurs with the assistance of a base. The transmetallation step is essentially an exchange between the organic group of the organoboron species and the metal complex. Finally, reductive elimination completes the catalytic cycle. In this step, a new carbon-carbon bond between two organic groups is formed, simultaneously regenerating the catalyst. For additional mechanistic aspects, check out this paper. For experimental procedures and a list of some of the most popular cross-coupling reactions, refer to the Chemists Cookbook. To carry out the reaction, I needed an organic halide and the organoboron reagent. However, the latter was not commercially available, so I had to synthesize it. One of the most convenient ways to prepare it is through the Miyaura borylation. The Miyaura borylation enables the synthesis of boronates by cross-coupling of bispinacolato diboron B2-pin2 with an aryl halide. Into a round bottom pressure flask equipped with a stir bar and loaded with 15 grams of diaryl bromide, I added 1.5 equivalents of B2-pin2 followed by 2.0 equivalents of potassium acetate under an argon atmosphere. Next, I added 140 milliliters of anhydrous 1,4-dioxane and bubbled the mixture with a stream of argon for 10 minutes. After that, I added 0.05 equivalents of palladium DPPF dichloride to the mixture and purged it with argon for an additional 10 minutes. I then sealed the vessel with a screw cap and allowed the reaction mixture to stir at 85 C overnight. After completion, I let the reaction mixture cool to room temperature and analyzed the reaction progress by TLC, using 50% ethyl acetate in hexanes as the mobile phase. The products were UV active, but I also revealed the TLC plate with potassium permanganate stain. All the starting material was fully consumed, and I could also spot some additional byproducts, mostly arising from the excess of B2-pin2. I filtered the mixture through a pot of silicate containing a small layer of silica gel at the bottom and rinsed it with ethyl acetate to ensure the elution of my product. I then evaporated the solvent to obtain a crude product, which I dissolved with ethyl acetate before adding silica gel to prepare the dry loading for my flash column chromatography. After evaporating the solvent, I transferred the silica gel loaded with my crude residue into a pre-column and purified my product by flash column chromatography. I use a gradient of ethyl acetate in cyclohexane, and when my desired product started to elute, as detected by the UV-Vis detector, it was collected into several tubes that I combined. After evaporating the solvent, I obtained my desired product as a brown solid. According to the NMR analysis, the product was slightly impure. The aliphatic region presented some additional peaks. The main impurities were derived from the excess of B2-pin2, which coeluted together with my product. I decided to repurify the product before moving to the next step. Finally, I obtained 15 grams of my product in 80% yield. The next step was the Suzuki coupling. Into a round bottom pressure flask equipped with a stir bar and loaded with 10 grams of diaryl bromide, I added 2.5 equivalents of cesium carbonate, followed by 1.1 equivalents of the boronic ester under an argon atmosphere. Next, I added 200 milliliters of anhydrous 1,4-dioxane and 22 milliliters of water and sparged the mixture with a stream of argon for 10 minutes. After that, I added 0.1 equivalents of palladium DPPF dichloride to the mixture and purged it with argon for an additional 10 minutes. I then sealed the vessel with a screw cap and allowed the reaction mixture to stir at 100 C overnight. The following day, I followed a similar procedure. After confirming the reaction's completion by TLC and performing the subsequent workup, I purified the crude residue by flash column chromatography to obtain 8 grams of my desired product in 75% yield. There are many different procedures to carry out these transformations. It is even possible to telescope the Miyaura borylation and the Suzuki coupling into a one-pot procedure. What reaction conditions do you usually use? How do you get rid of B2-pin2 byproducts? Let me know in the comments.